Adding, subtracting, and multiplying complex numbers. By now, you're quite familiar with complex numbers. In an earlier video, I introduced them as an extension of real numbers. So they extend in the complex plane. They are two-dimensional numbers. So if you have not seen that video, maybe you want to watch that first. Now there, we learned that every complex number could be written with a real part like A and imaginary part, say B. And then you put an I. So every complex number has this form, A plus BI. And we looked at some examples. We did see them plotted on the complex plane. So you can replace A and B with any real numbers. So let's write down a few examples. So if I take A to be 2 and B to be 3, then 2 plus 3i. It could be negative 3 plus 4i. Or I may just have 5i. In that case, the real part is 0. In fact, all the real numbers are also complex numbers. Their imaginary part is 0 there. So in this video, we'll be talking about adding, subtracting, and multiplying. Look, I have avoided dividing complex numbers in this video because it's a little bit more complicated, and there will be a separate video just for dividing complex numbers. Adding and subtracting of complex numbers is extremely easy. In fact, it's something that you have already done whenever you combine two linear expressions. So, what do I mean by that? Let me start with some examples. So, let's say I have two complex numbers, say 3 plus 10i, and then the other complex number, let's say it's 5 plus 2i. So if you need to add these two, it's a matter of combining like terms. Think about what you would do if you had something like 3 plus 10x and 5 plus 2x. You combine the like terms. You say 3 and 5 could be combined to become 8, and 10x and 2x could be combined to become 12x. In fact, it's exactly what you'll be doing here. The process is identical. So you combine the real parts, 3 plus 5 is 8, and you combine the imaginary parts. 10 plus 2 is 12. So 10 plus 2, 10i plus 2i is 12i. So that's our answer. So really, adding or even subtracting works the same way. So let's put some negative numbers as well. So say negative 2 plus 3i, I mean negative real or imaginary parts. And then say I have 1 minus 5i. So now if I'm looking to combine the real parts, negative 2 plus 1 is negative 1. And then 3i minus 5i is negative 2i. All right, so that's about addition. What do you do when you have to do subtraction? Say this time I have negative 3 plus 2i and subtract 4 minus i. So if you try to combine the like terms this time, it's negative 3, but remember negative 3, and you might say that this is positive 4. But there is a negative outside, which you need to distribute. So let's go ahead and break open the parentheses. So here, I don't have a negative sign, which means this negative 3 plus 2i stays as it is, whereas I got to distribute the negative. So this turns this into negative 4, and the negative I would turn into positive I because you're multiplying by negative. Negative times negative is positive. Now there are no parentheses to break. It's just a matter of combining like terms. Negative 3 minus 4 is negative 7, and 2i plus I is 3i. So that's our answer for 3. Let's look at one more. Maybe 5 minus 6i subtract negative 2 plus 3i. All right, as usual, we will break the parentheses 5 minus 6i and distribute this negative. So negative of negative 2 is positive 2, and negative times positive is negative. So it becomes negative 3i. So you might notice when you distribute negative, it flips the signs inside the parentheses. So negative 2 became positive 2 and positive 3i became negative 3i. And now you can combine the like terms. 5 plus 2 is 7. Negative 6i minus 3i is negative 9i. So since it's nothing more than combining linear expressions like that, there's hardly any work. Adding and subtracting. Now multiplying is what we will look next. If I have two complex numbers that I want to multiply, say 2 plus 3i, and I want to say take 4 plus 2i. Let's do that. Now, if you remember what you did when you had two binomials, 2 plus 3x and 4 plus 2x, sometimes you called it FOIL method. You would multiply the first, so each term here gets multiplied by each term over there. Now, it's exactly the same process here. So you multiply 2 with both of these, and then you multiply 3i with both of these. So let's do that. 2 times 4 is 8. Plus, you multiply 2 times 2i. 2 times 2 is 4, so 2 times 2i is 4i. And now you multiply 3i with 4. 3i times 4 is 12i. And sometimes this is where students make mistake. Notice, if you are multiplying 3i with 2i, 3 times 2 is 6. But you have to multiply I times I. It's not I. I times I is I square. Now, you remember this idea. I square equals negative 1. So I'm putting that again in a box here. So when you use that, you can simplify this last term. So I can rewrite my expression. So let me just change this to negative 1. 8 plus 4i plus 12i plus 6. 6i square means 6 times I square, but I square is negative 1, so I'm going to write 6 times negative 1. Now at this point, I can combine the like terms. So 8 cannot be combined with either 4i or 12i, but this is actually negative 6. Maybe let's go ahead and write that. At least in the first problem, I like to write out all the steps. So now, we don't have any parentheses, no more multiplications to be done. It's just additions and subtraction. So that's when we say we combine the like terms. 8 can be combined with minus 6. So 8 minus 6 is 2. And 4i plus 2i is 16i. So that's our answer. All right, let's do one more example. Oh, before we actually move on to the next example, I want you to notice whenever you have a term involving I square, what ends up happening is that term, you can simply ignore the I square part, but since it's negative 1, the sign would be flipped. So you had a plus 6i square, that all of that turns into negative 6. If it was negative 6i square, I would have had positive 6. So that's what you want to pay attention to. And in this example, example 6, let's move quickly from here to there, skipping this step. Now, say I have negative 1 minus I times 2 plus 7i. So let's multiply negative 1 times 2 is negative 2. Negative 1 times 7i is negative 7i. The negative I times 2 is negative 2i. And negative I times 7i, it's positive 7i. So negative times positive is negative. But I times 7i is 7i square. Since I'm multiplying two copies of I get I square. So what does that simplify to? Now recall, negative 7i square simply becomes positive 7. And that's what I'm going to write in this step. So negative 2 minus 7i minus 2i, and this one is positive 7. So negative 2 plus 7 is 5, minus 7i minus 2i is minus 9i. That's our answer. Now, let's look at one other example. Say I have 3 minus 4i and 3 plus 4i. So let's do the same thing that we did in the previous two examples. 3 times 3 is 9. 3 times 4i is 12i. And negative 4i times 3 is negative 12i. And negative 4i times positive 4i is negative 16, because 4 times 4 is 16. And I times I is I square. So this is positive 16. And actually, you might notice there's a 12i minus 12i. I could cancel them out, and then I have 9 plus 16 equals 25 for my answer. All right. Now I'm going to define a new term. And it's called conjugate complex numbers. So what are conjugate complex numbers? Well, let me give you an example first. So what's an example? Something like 2 plus 7i and 2 minus 7i. These are conjugate complex numbers. Why? What do you notice? Here they have the same real part, 2, but the imaginary part for this complex number is 7, positive 7, and the imaginary part for this is negative 7. So these complex numbers have the same real part but opposite imaginary part. Let's write one more example. Say negative 5 plus 3i and negative 5 minus 3i. These are two complex conjugate numbers. Now, why do we care to define conjugate complex numbers? Yeah, there are these two numbers that have same real part and opposite imaginary parts. So what, you may ask? Why do we care? Now, here's why. Notice when you add these two, so let's go ahead and add the first complex conjugate pair, 2 plus 7i and 2 minus 7i. Then what do you get? Well, 2 plus 2 is 4, but 7i minus 7i, they cancel each other out. So that's our answer. Now, if you were to carry out the same thing with this next pair, then negative 5 minus 5 is negative 10. And look, plus 3i and negative 3i, they cancel each other out. So this is, in both of these cases, I got 4 and negative 10. In fact, it's because they have opposite imaginary parts. The imaginary parts cancel each other out. So that's why I just have a real number, 4. Here I have negative 5 and negative 5, negative 10, because the imaginary parts cancelled each other out whenever I added two conjugate complex numbers. So not only their sum is a real number, but let's look at an example of multiplication that we did earlier. So look at example 7. Look at these two complex numbers, 3 minus 4i, 3 plus 4i. And what do you notice? Your answer was 25. So your final answer did not have an I in it, which means it is real number. So it looks like when you add two complex conjugate pairs, it's easy to see that you always get a real number. But in this case, when we multiplied, then also we got a real number. So is it just a coincidence or can we prove? So let's take in general, so let's not take any special conjugate pairs. So say I have a plus bi. Now what is the conjugate of this complex number? It got to have the same real part, which is a, but opposite imaginary part, minus bi. So now let's go ahead and multiply. A times a is a square. A times negative bi is negative abi. And now we multiply bi with both of those terms. Sorry, bi with each of these terms. What is bi times a? So let me just write this as bia. And then I have positive bi with negative bi. That's negative. B times b is b square. And I times I is I square. So what do you notice? Do you notice that these two middle terms are opposites, abi, and this is also abi. With multiplication, you can switch the order. You can put the a in front. So these two cancel each other out, and what you are left with, the final, the first and the last terms, the ones at the end. So this is a square, and notice, what does I square do? It flips the sign in front of b square here. So this becomes a square plus b square. And look, there is no I in it. So this is the reason why we care to talk about conjugate complex numbers, is because when you add or when you multiply two complex conjugate numbers, you always get a real number. And in fact, this is going to be a square plus b square. And this is going to be what's used in the next video, which is on dividing complex numbers. So sometimes you don't want to have an imaginary part. You don't want to have I. So this is the idea that we will be using. So that's all I have for this video, and this is really simple, and I have some practice problems. So let me tell you what they are. So the practice problems, I have 6 problems on adding or subtracting, and actually 3 on addition and 3 on subtraction. So that's just a matter of combining like terms. Here also in multiplication, it's just about foiling, but you go a step further because I square is -1, and you eventually end up with a complex number. So your final answer will also look like a plus bi. And the answers will be there in the video description. And that's it for now. Good luck, and I'll see you in the next video. Thank you.